Hi folks! The following video talks about two new reactions of alkenes known as hydroboration-oxidation and hydrogenation. I want to start by talking about the regioselectivity of hydration reactions, ones where you're adding an H and an OH group across an alkene. Depending on where the H and OH add, you can have either Markovnikov or anti-Markovnikov addition. So far we've seen two examples of hydration reactions. One is acid-catalyzed hydration. In this mechanism, carbocation rearrangements can occur. Another method of adding H and OH groups is known as oxymercuration-demercuration. This adds the OH group to the more substituted carbon of the alkene, and there is no carbocation formation in this mechanism, so carbocation rearrangements are not possible. For both of these reactions that we've covered so far, these are Markovnikov regioselectivity. The H is added to a less substituted carbon, and the OH group adds to the more substituted carbon. What the first part of today's video is going to look at is a reaction for giving anti-Markovnikov hydration. Here you're imagining adding the H and the OH group again, but the H is added to the more substituted carbon. You could draw it out here in the product if you wanted to. And the OH group has added to the less substituted carbon. We need a new set of reagents to achieve this selectivity. The method for anti-Markovnikov hydration, which results in formation of an alcohol, is known as hydroboration-oxidation. The reagents for this come in two steps. Step 1 is treatment of the alkene with BH3 THF. I'll explain on the next page what this looks like. And then step 2, make sure this is a separate step. You add H2O2 and NaOH. The net effect is that a hydrogen is added to the more substituted carbon of the alkene, and the OH group adds to the less substituted carbon of the alkene. I would say that the regioselectivity for this reaction is anti-Markovnikov. I selectively form the constitutional isomer of product with the OH group added to the less substituted carbon. In terms of the stereochemistry of the reaction, this is different than reactions we've seen before. The H and the OH group are added in what's known as a syn addition. This means that these two groups add to the same face of the alkene. An example reaction where this stereochemistry becomes apparent is shown below. In both of the products, I've added the OH group to the less substituted carbon of the alkene, so it shows up on the bottom right in each case. This indicates that anti-Markovnikov selectivity. And for the stereochemistry, I've needed to show the syn addition. So, the right two carbons of the alkene are starting out. One will get a hydrogen, the other will get the OH. To show the syn stereochemistry, I need to draw these H and OH groups that have added, both as dashes, and then both as wedges. Before talking about the mechanism, I want to talk about the role of BH3. BH3 looks a lot like the methyl carbocation CH3+. Both structures feature a central atom with 3 hydrogens around it and an empty p orbital. The boron and the carbon are both trigonal planar due to their sp2 hybridization, and the p orbital has lobes above and below the plane of these molecules. Because of its empty p orbital, boron has an incomplete octet, and it is very electrophilic. It can react with nucleophilic solvents to form more stable compounds. So typically, rather than dealing directly with BH3 itself, which is a toxic and flammable gas, most chemists will use a combination of BH3 and THF, a cyclic ether solvent. The BH3 reacts with the THF solvent reversibly, where THF can use a lone pair to donate electron density into boron's empty p orbital. After this nucleophilic attack, a new oxygen-boron bond forms. Oxygen has 3 bonds and a positive charge, and boron has 4 bonds and a negative charge. This compound is known as BH3THF. And because the BH3 in it is less reactive, it is a more convenient source of BH3. But whenever you see this BH3THF, still think about the boron in it as being an electrophile. I want to start by talking about what's known as the hydroboration step in the mechanism. This is the step that involves treatment of the alkene with BH3 or BH3THF. And the outcome of this step is that boron adds to the less substituted carbon of the alkene, and hydrogen adds to the more substituted carbon of the alkene. There are 2 stereoisomers of product that form, either where the new H and BH2 groups are both wedges, or where the new H and the new BH2 are both dashes. For keeping track of where the boron and hydrogen are adding, I'm going to start by imagining rotating our alkene so that we're looking at it sideways. The cyclohexyl ring is supposed to be coming out at you, and the methyl and hydrogen groups are pointing away from you, into the page. The hydroboration mechanism is a new one. It's going to have 2 curved arrows for a reaction that occurs in a single step. What you're going to do is take the electrons from the pi bond and bring them to boron, which has an empty p orbital, and then you take the electrons from the BH bond and bring them to the more substituted carbon of the alkene. At the transition state, there is a ring of 4 bonds that are breaking and forming. The pi bond is breaking, a carbon-boron bond is forming, a boron-hydrogen bond is breaking, and a carbon-hydrogen bond is forming, all in the same step. So, these bonds are breaking and forming all at the same time, so I can call this step concerted, but the extent to which they're breaking and forming differs. The carbon-boron bond forms faster than the carbon-hydrogen bond. Because these bonds are forming to different extents, I would call this asynchronous in terms of the bond formation. And this uneven bond formation leads to some partial charges. Because the hydrogen is late in being delivered to carbon, the carbon has a partial positive charge, because it's losing its pi bond more than it's gaining its new bond to hydrogen. And there's also a partial negative charge on boron. It looks more like a boron with 4 bonds than a boron with 3 bonds, which would be neutral. After this step, the carbon-hydrogen and carbon-boron bonds have completely formed, and the pi bond has completely broken. Because this all occurred in one step, at the transition state, both the hydrogen and boron were adding to the same face of the alkene, so they would both point in the same direction in the product. This means that a syn addition has occurred. I could also rotate my product so that it looks more like my original structure, and because I brought in the BH3 molecule from above the alkene, I would draw the carbon-hydrogen and carbon-boron bonds as both wedged. Alright, so this is one possibility. I've just shown the reaction where I've added boron to the less substituted carbon and hydrogen to the more substituted carbon. What if instead I brought in the BH3 from the top of the alkene again, but what if I put boron closer to the methyl side and hydrogen closer to the hydrogen side of the alkene instead? My mechanism would still have two curved arrows. I would take the pi electrons to boron, take the electrons from the boron-hydrogen bond, and bring them to the carbon of the alkene. In this case, at the transition state, I'm forming a bond between the less substituted carbon and hydrogen, and a bond between the more substituted carbon and boron. Here as well, the formation of the carbon-hydrogen bond is lagging behind the formation of the carbon-boron bond, and so I've drawn this dotted line as longer. The carbon to which the hydrogen is getting delivered has partial positive charge because it's late in getting that hydrogen, and boron has a partial negative charge. It looks more like it has 4 bonds than 3. The product formed from this step would have the pi bond completely broken, the BH2 group added to the more substituted carbon of the alkene, and the hydrogen added to the less substituted carbon of the alkene. To make my molecule look more like the original structure, I could rotate it so that the boron is a wedge, the new hydrogen that's been added is a wedge, and the methyl group is now a dash. The hydrogen and boron have both still added to the same face of the alkene, but now I've added the boron to the more substituted carbon. Does this actually occur? It turns out that this potential product, where you've added BH2 to the more substituted carbon, is not observed. We'll have to look at the transition states for these two potential reactions to figure out why this is the case. The transition state leading to the anti-Markovnikov product, in which boron has added to the less substituted carbon of the alkene. At the transition state, the partial positive charge is on a carbon with 3 other carbons attached to it, meaning it's partial positive on a tertiary carbon. Again, this partial positive charge is arising because the carbon-hydrogen bond is not very formed. So this carbon looks like it has more like 3 bonds instead of 4 because that hydrogen is so late in arriving. So, if we add the hydrogen to the more substituted carbon of the alkene, we get partial positive charge on a tertiary carbon. What about the bottom case, where we're looking at adding hydrogen to the less substituted carbon and boron to the more substituted carbon? This would be the Markovnikov addition product, but it turns out it is disfavored. One reason that it's disfavored is that the carbon that's getting the new bond to hydrogen is secondary instead of tertiary. And because of this, the carbon with the partial positive charge at the transition state is secondary instead of tertiary. Similar to full carbocations, it is more stable to have partial positive charge on a tertiary carbon than a secondary one. Another factor that makes this transition state less favorable is the fact that BH2 is larger than hydrogen. In the first transition state, we were putting a small hydrogen near the bulky methyl group of the alkene, whereas in this bottom case, we're putting a larger BH2 group closer to a larger methyl group. There is steric clashing between the methyl and the BH2 group being added to it. So this is a second factor that makes it less favorable to add the boron to this more substituted carbon. So far, I've looked at 2 different possibilities for the way we add the BH3. I compared transition states and determined that the product where the BH2 group is added to the less substituted carbon is favored, both based on partial positive charges at the transition state and based on sterics at the transition state. Now we want to consider the stereochemistry of the products that formed. So far, I've only shown the pathway to get to the product where the H and the BH2 group are both wedges, and I haven't yet accounted for how I make the product where both of those groups are dashes. To get to the product where both groups are wedges, I brought in the BH3 group to the top face of the alkene. In order to show the product where both the H and BH2 groups are dashes, I need to bring in the BH3 to the bottom face of the alkene instead. I'd draw my two curved arrows, the first one from the alkene to the electrophilic boron. Then I would take the electrons from the boron-hydrogen bond and bring them to the carbon. At the transition state, I have the pi bond breaking. The carbon-boron bond is mostly formed. The boron-hydrogen bond is breaking, and the carbon-hydrogen bond is only just starting to form, so I've drawn this bond as longer. As usual, the carbon that's getting the hydrogen attached to it has a partial positive charge at the transition state, and boron has a partial negative charge. After this step, the pi bond has broken, the carbon-boron bond has formed, and the carbon-hydrogen bond has formed. Because this all occurred in a single step, the H and the BH2 were added to the same face of the alkene, and I would call this a syn addition. If I wanted to rotate this molecule around to make it look more like my original molecule, I could rotate it such that the methyl group is a wedge and the boron group is a dash. This is that second structure from my reaction shown up above. If we compared the stereochemistries of the two products, adding the BH3 to either the top or the bottom of the alkene, you would see that both products are enantiomers of each other. So, that first step, the addition of hydrogen and BH2 to the alkene, is called the hydroboration step, and the second step is treatment of the resulting boron-containing molecule with H2O2 and NaOH. This oxidation step has the effect of replacing the BH2 group with an oxygen in exactly the same position with the same stereochemistry as the group bound to boron had before. As a heads up, this mechanism is going to look pretty different from ones that we've seen before. The mechanism begins with a proton transfer between the H2O2 and NaOH reagents. The hydroxide acts as a base to deprotonate one of the OH bonds of H2O2. This forms HOO- and water. Based on the pKa's of H2O2 compared to water, it is this product side of the proton transfer equilibrium that is favored. This negatively charged oxygen of the conjugate base is a nucleophile, and the boron with 3 bonds is an electrophile. I'll have a nucleophilic attack where I take a lone pair from the anionic oxygen and bring it to boron. The electrons from oxygen were donated to generate a new oxygen-boron bond, and now boron has 4 bonds and a negative charge. The next step of the mechanism is an unusual rearrangement step. I'm going to take the electrons from the carbon-boron bond and bring them to oxygen. This has the effect of breaking the carbon-boron bond. And then I'm going to break the oxygen-oxygen bond and bring those electrons to the far oxygen with the hydrogen on it. This step breaks the oxygen-oxygen bond and forms hydroxide, and the arrangement of the oxygen in the boron has changed. Notice before it was carbon-boron-oxygen, and now it is carbon-oxygen-boron. Importantly, when this step occurs, the stereochemistry doesn't change. So if you had a wedged bond to boron before, you still have a wedge bond now to oxygen. Now that the boron has 3 bonds again, it is an electrophile again, and the OH- that we just made can serve as a nucleophile. I'll bring a lone pair from OH- to the electrophilic boron to form a new bond. After this nucleophilic attack, there is a new oxygen-boron bond made with electrons from OH-. Boron is back to having 4 bonds and therefore has a negative charge. The next thing that's going to occur is I'm going to break the boron-oxygen bond to the oxygen with the carbon groups on it. To do this, I'm going to take the electrons from the boron-oxygen bond and bring them to oxygen. This is a loss of leaving group, and I'm bringing the electrons to oxygen instead of boron because oxygen is more electronegative. After this step, I have an anionic oxygen, and I have a boron with 2 hydrogens and an OH group. Because the boron has 3 bonds, it is neutral. The last step to get to a neutral alcohol product is to do a proton transfer. For the acid, I'm going to use water. I'll use a lone pair of the O- to deprotonate water in the proton transfer step. And this final proton transfer forms the alcohol product. So everything I drew in this mechanism was for the enantiomer of starting material with a wedge BH2 group. After this mechanism, that wedge BH2 has been converted into a wedge OH group. If instead you'd started with the other enantiomer of starting material, in which you had a dash BH2 group, you would get the product where you have a dashed group to OH. So to do a quick summary on hydroboration-oxidation, the first set of reagents, BH3THF, are the hydroboration step of the mechanism. This step shows anti-Markovnikov regioselectivity, meaning hydrogen adds to the more substituted carbon of the alkene, and boron adds to the less substituted carbon of the alkene. Syn addition of the H and BH2 groups occurs. So in this product, both either appear as wedges or both appear as dashes. The second set of reagents to get to the alcohol product is known as the oxidation step. You treat the boron intermediate with H2O2 and NaOH. This has the effect of replacing the BH2 group with an OH group with the stereochemistry maintained. I want to show a few examples of predicting the products for hydroboration-oxidation. Here's an example of a monosubstituted alkene starting out, and I'm treating it with the 2 reaction steps for hydroboration-oxidation. To start out, I like to draw the product without worrying about stereochemistry, so I would add the hydrogen to the more substituted carbon of the alkene, and the OH group to the less substituted carbon of the alkene to show the anti-Markovnikov regioselectivity. In this particular example, no chiral centers have formed. I could draw the product without having to worry about showing wedges and dashes. Here's another example, this time featuring a di-substituted alkene. I would first draw the product without worrying about stereochemistry. I would add hydrogen to the more substituted carbon and oxygen to the less substituted carbon. Notice in this case, I've formed one new chiral center, where the hydrogen has added. In this case, I do need to worry about showing stereochemistry. For that new chiral center, I could draw one of its bonds as a wedge, or one of its bonds as a dash, to show that 2 enantiomers of product have formed. Last, let's consider a tri-substituted alkene starting material. Here it is the carbon on the right that is less substituted and will get the OH group. I would draw the product where I've added the OH group in an anti-Markovnikov fashion to the less substituted carbon, and hydrogen has added to the more substituted carbon. I didn't worry about stereochemistry to start, but now I need to check, did I form any new chiral centers? In this case, I have formed new chiral centers, and I've actually formed 2 of them. When you form 2 new chiral centers in a hydroboration oxidation, this is where you need to be really careful in drawing your 2 products where syn addition has occurred, where the H and the OH group that have added were added on the same face of the alkene. Where in one case, the methyl group would be a dash, and the H group and OH group would be wedges. It is this H and the OH group that have added syn to each other. And in the other stereoisomer of product, the H and the OH group that were added are both dashes, making the methyl group a wedge in this case. So it's optional to draw out this hydrogen that's been added, but I've done so here just to emphasize the stereochemistry and the fact that the H and the OH group added to the same face in a syn addition fashion. Another reaction that occurs by syn addition is known as hydrogenation. In this case, we'll be looking at adding 2 hydrogens across a pi bond, such as you have in an alkene. Hydrogenation requires a transition metal catalyst. The textbook uses 3 examples of these. Either platinum, a catalyst known as palladium on carbon, which is written as PD/C, or a nickel catalyst. These alkene hydrogenation reactions occur by syn addition, meaning both hydrogens get added to the same face of the alkene. As an example, let's consider this tetrasubstituted alkene. Here I'm treating this with hydrogen gas and platinum, the catalyst. This hydrogenation results in the formation of 2 new chiral centers, where both of the carbons that had hydrogens added to them are chiral. When you get 2 new chiral centers in a hydrogenation, you need to draw the products to make it clear that syn addition of the hydrogens has occurred. I can do this by showing both hydrogens added as dashes, or both hydrogens added as wedges. Notice I was careful in each case that each chiral center has 2 lines, a wedge, and a dash. Here's another example of a tetrasubstituted alkene being treated with hydrogen gas and platinum. Here as well, the hydrogens get added to the same face of the alkene. If both hydrogens added from below the alkene, both new bonds to hydrogen could be drawn as a dash, and both methyl groups could be drawn as wedges. So why am I not drawing another product where the 2 hydrogens are wedges and the 2 methyl groups are dashes? That is because the product that I've formed is a mesocompound. It contains 2 chiral centers, but there is a plane of symmetry within the molecule. This mesocompound does not have an enantiomer, so I would form this as a single product for this reaction. It would also be fine, though, to draw the product where both hydrogens were wedges and both methyls were dashes. That's actually the same compound. And for a last case, let's look at a disubstituted alkene, again being treated with hydrogen gas and the platinum catalyst. In this case as well, I add 1 hydrogen each to the 2 carbons of the alkene, and then I need to consider the product stereochemistry. One of the carbons that had a hydrogen added to it is not a chiral center, but one of them is. It has a methyl group, an ethyl group, a propyl group, and a hydrogen attached to it. When this is the case, you need to draw 2 enantiomers of product. You could do this by showing one group as a wedge and another group as a dash, and then switching those wedges and dashes in the other product. For hydrogenation, I won't discuss the mechanism, but I do want you to know that it proceeds by syn addition. You should know the reagents for hydrogenation and be able to predict the products. Alright, so in summary, today's video talked about two reactions that lead to syn addition. One of these is hydroboration-oxidation, which results in anti-Markovnikov addition of H and OH groups to an alkene. And the other reaction is hydrogenation, the conversion of an alkene into an alkane by addition of hydrogen across the pi bond of the alkene. That's it for this video. I will see you in class.